So a lot of this information I think you already have or you already know from the few activities we've done through this. So this is going to be much more a review. So if I go over something a little too fast, note there is a copy of these notes in Schoology, and later on today there will be a video link to these notes. So if you ever miss something and need to go back, you can always do that. So the biggest thing when it comes to the theory behind how this works, we call it VSEPR theory. You want to be familiar with VSEPR theory. And the name is somewhat explanatory. Kind of explains itself. I don't know the exact word. It's that the outer shell electrons, the valence electrons, bonds are made of electrons. The electrons repel each other. And this attempts to explain their behavior. And so this is kind of how we came up with what these molecules look like. This understanding that when these things are bonded together by electrons, and electrons are all negative, they're going to repel, and they're going to get away from each other as far as possible. And so when you have these little tiny magnets that the electrons kind of become in 3 dimensions, the shapes that we've gone over, right, the ones on the back of your orange sheet, linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, bent again, like that's what they turn out. And then when we look at these molecules, like that's how they actually are. And so VSEPR theory just tries to explain why molecules form the shapes that they form. Obviously, you need to know the shapes. Now, all of this information, I would say you don't need to write down because it's on the back of your orange sheet. But you do need to know the shapes, and this idea of understanding bonds and lone pairs and being able to, from your Lewis structure, be able to determine what they are is going to be important. And one of the things that you were doing on page 16 and 17. One of the things that's important to know just about lone pairs, and you should have hopefully realized this from the simulation, is that when we take a molecule in the model, the degrees should be 109.5. Right, that's in a tetrahedral molecule. No, the angle between the 2 bonds is 109.5. So every angle, they're as far away from each other as possible. But when you change those to a lone pair, in the little simulation that we did before, you might have noticed the angle didn't change. But when you switched it to real molecules, it squished it a little bit. Because a lone pair has a little bit more of a repulsive force than a pair of electrons that are involved in bonding. And so that's why it's important to take into account the lone pairs, because they can distort the angle of the molecule's bonds and thus give it a different shape and change the shape generically. The next thing you want to write down is this, that there are some exceptions to the octet rule. Definitely write down that group 3 is an exception. So group 3, we're looking at boron, aluminum, gallium, indium, thallium. When those elements bond covalently, they don't need 8. They only need 6. Now this is easily explained, however, we have not learned the chemistry to explain why this is okay and they can get away with only having 6. Just know that if you have a group 3 element, that's going to be an exception. The other one that you might see is group 2. I'll leave that as optional to write down, but group 2 only needs 4 electrons. So every now and then beryllium will bond covalently, and we'll get into like how we know that here in a second. You know, we've talked about how ionic is always just metal and non-metal. Well, that's not technically true. There are situations. So group 3 is the main one that you'll see, and then every now and then potentially group 2 pops in there. And they're just exceptions to the octet rule that you want to have down. And that's it. That's all that I wanted you